I welcome everyone to this video. I'm Mr. Ish. Thank you for joining me. We're looking at the mechanism involved behind this reduction process. What do we have here? The Wolff-Kishner Reduction. We have over here a ketone which will be converted into an alkane. This right here is your end result is going to be an alkane, and it will be this RCH2, or you have two different R groups as you see. Your carbonyl is going to be converted into CH2, and this is your complete reduction procedure. Your Wolff-Kishner reduction, you can symbolize as WKR, will involve a workup procedure which is not part of this officially, but that workup procedure will require hydrazine, NH2 in the presence of an alcohol. Then the step number 2 is your actual reduction procedure, in which you will have a strong base, sodium hydroxide, then you'll have triethylene glycol, and we'll just write it out, triethylene glycol medium and strong heat. That will complete the reduction procedure, but you have to start with this. This right here is not officially part of this reduction procedure, but the end result from here then begins that reduction procedure, hence step number 2 involves that. So let's examine this. Keep in mind, when you are doing this, step number 1, you're going to do NH2. What you will end up seeing is this. The hydrazine will add to your carbonyl functionality in the following way, but this is not the mechanism. I'm just showing you the brief item over here, and it looks like this. This right here will now begin your WKR procedure, your reduction procedure, and then when you take it all the way through with the items there in step 2, sodium hydroxide, a strong base, triethylene glycol, and heat, then you will take it to your alkane RCH2R, assuming that these R groups here were hydrocarbons. So this is going from this to this, and this right here is the official part of your reduction procedure. So let's examine the mechanism involved. And the first step, which is not officially the Wolff-Kishner reduction procedure, but it starts up your item which you need for that reduction, you're doing, in the presence of alcohol medium hydrazine, you're going to apply that into your ketone. This here is a ketone. When you do it, what you will see is your hydrazine will add over here, and you see it right here, and the R group over here. Let's not forget our lone pairs of electrons, because you need to see them all for the mechanism. This is exactly what it looks like. You have that, but what happened to this hydrazine? I have a hydrazine which looks something like this. Here's your hydrogen, here's your hydrogen, here's your hydrogen, your hydrogen. You have lone pairs of electrons as I'm demonstrating. Look, this oxygen and this hydrogen are going to drift away as what? They'll drift away as a water molecule. It's drifted away. This nitrogen is that nitrogen over here, then that NH2 is what you see over here. The hydrazine adds to your carbonyl in the manner such that 2 of the hydrogens from hydrazine and the oxygen from the carbonyl will go away as your water molecule. Everything else you see will now begin your official reduction procedure, your Wolff-Kishner reduction, and now you have to start showing all the electrons because you need to see them. To demonstrate the mechanism of the WKR, your Wolff-Kishner reduction, you want to show the hydrogens like this. You know, I've showed you earlier that you need a strong base, sodium hydroxide, and you need to see it. What will sodium hydroxide do? When you are looking here at sodium hydroxide, it will act as a catalyst of this reduction procedure. You have your sodium hydroxide in the presence of a water, and you know you're going to generate a hydroxyl anion because it's going to pluck a hydrogen from water because it's a strong base. You're going to look at this hydroxide anion, and it looks like this. The sodium hydroxide is acting as your catalyst. This right here is going to pluck your hydrogen away to generate a water molecule. The 2 electrons of this nitrogen hydrogen bond will come here into the nitrogen, and what you will see is this. I will demonstrate everything else without any other change. I'm just making this arrow small because you need to see what is happening over here. You have that nitrogen, it's unaffected. Then I have this nitrogen, I have the hydrogen attached to it, this hydrogen unaffected. The 2 electrons coming from this bond and the 2 original electrons, the lone pairs on the nitrogen. Now you have an excess charge on that nitrogen, and there's a negative charge. There it is. The water molecule has drifted away because the hydroxide, which generated originally from your sodium hydroxide effect, has now snatched a hydrogen because the hydroxyl snatched the hydrogen, generated a water molecule. In essence, when you're looking at your compound, which was something like this, and you see it now, you can say here your hydrazine prepped compound. You will say here sodium hydroxide. You can even put here a water molecule, triethylene glycol. I'm just writing TRG, and then heat. This right here is probably important to show because the water molecule was necessary to generate the hydroxide anion in the presence of the strong base. So it's important to show there's a water required as a reactant. Now you're over there. We have this other R group, and let's not forget that. You will have a shuffling of electrons. These two electrons here will shuffle over here, generate a double bond. These two electrons will break, and the electrons of those two bonds, the single of this duplex, will come here to the carbon. What does it demonstrate? You're seeing this. I have here now the negative charge come right here on carbon, the carbonyl carbon. The negative is transferred from here to here by means of shuffling of electrons. The double bond will be here between the two nitrogens. You still have the hydrogen. You only have now one lone pair of electrons here. You have one lone pair of electrons here. The original here, and you have the other R group. This is where we are. What happens over here? This right here is interesting to see because from here, the shuffling of electrons to here, and these are kind of resonance structures. You can go back and forth, but this right here will demonstrate the next step. What exactly is that next step? You have a water molecule floating around in the medium, and the carbonyl carbon, which is no longer a carbonyl carbon, but it's a carbanion. It will snatch this hydrogen. The two electrons here will come here to the oxygen, and you've generated a hydroxide anion, and the hydrogen has come attached to this carbon over here. And now you're seeing this R. I have a C, then I have this nitrogen, double bond N, my lone pair of electrons. You have to show the lone pair of electrons because of shuffling effects. You don't want to miss them out. And then you have the hydrogen. Here's your hydrogen over here, and you have your other R group. This is where we are. There's no charge on this compound. It's neutral. What happens now? We have to somehow get rid of this hydrazine compound and get a hydrogen over here so we can come to our this end result, which you know what going to be RCH2 and then R. The carbonyl original is going to become a CH2. You're looking here at an alkane to come into the play. You have to now utilize this. Here's your hydroxyl, which is just generated over here. This hydroxyl is going to come into the reaction mixture. It has a negative charge. It's going to snatch the hydrogen over here. The two electrons are going to come onto this nitrogen over here. When it snatches that electrons, you're going to develop here a water molecule. Look how the water originally is formed over here at the start of the reaction. Then by the presence of the base, it became a hydroxyl and hydroxide anion. Then you're having the carbanion effect, looking at a water molecule generating another hydroxide anion. The hydroxide anion is coming over here, snatching another hydrogen from your nitrogen compound. And then you're looking here at a water molecule develop. So it's back and forth, hydroxide, water, and it happens that way. Now you will see an excess of charge on that nitrogen, and this is where you are. Here's your hydrogen, which was pulled off from the hydrogen from the water right over here on the carbon. You have this. Your hydrazine compound now looks something like this. The two electrons of this bond went back to the nitrogen, and it's right over here. And you see this. The water molecule has generated the hydroxide, snatching that hydrogen. This is where we are. Now this right here will go to reaction completion. How will it go through reaction completion? I have over there an excess of charge on that single nitrogen. You know what you're thinking over here. You can have a byproduct nitrogen. Diatomic nitrogen will come off. What does diatomic nitrogen look like? It looks like this. Triple bond N with two lone electrons on each side. And you're almost there. How will you develop that? You will have here a shuffling of electrons to arrive at this byproduct. These two electrons will come over here to generate that third bond, the triple bond between nitrogen and nitrogen, and then this bond will break. The electrons will be retained over here by the carbon. Keep that in mind. And your nitrogen will be given off. When your nitrogen is given off, it's just diatomic nitrogen, but it's a triple bond, and it will look something like this. Nitrogen triple bond with two lone electrons on each side, and there's nothing lost. I have one lone electron here, pair. I have one electron pair here, the lone electron pairs. The second excess pair of electrons generated a triple bond. Now I'm going to erase some items over here to generate the structure which comes off next. You know, with the carbon retaining the two electrons of this, you're looking here, yet another carbanion develop. I've erased a bunch of items here. You're going to come over here. I have your diatomic nitrogen already demonstrated. Now you're looking at your main molecule. It will look like this. You have your carbanion over here, and you have your hydrogen, you have your R group over here. This is where we are. This right here is the last step before completion. Keep in mind the diatomic nitrogen has gone away. The two electrons of this carbon nitrogen bond have ended up over here. You have here now another water molecule. and it looks something like this. This will snatch the hydrogen and you'll come back over and regenerate your base. When you do that, you have here the RCH2R. Here's your end result. You have regenerated your base OH minus, and it's regenerated. That's your end result. Two end results. This, your RCH2R, your alkane, and your hydroxyl. Your carbonyl functionality is converted to CH2. You have regenerated your base. Originally, you started with a sodium hydroxide in the presence of water, which was no different than just saying hydroxide anion, and it was used in the first step. But now we've regenerated the hydroxide. I'm erasing it because it's not involved in this particular step, but it was involved at the very beginning. So your mechanism comes to an end, and you see it, and it's done. Now that the mechanism is complete, let's just show you a quick reaction in a very summarized format. That'll be the end of the video. We're starting here with a ketone. I'm going to react this with NH2 hydrazine in an alcohol medium. What will I have? I'll have the hydrazine compound develop, and it will look something like this. What was given off here? A water molecule. This oxygen and two of these hydrogens here will give off your water molecule, and you're over there. Now we'll do the official Wolff-Kishner reduction. Wolff-Kishner reduction, the reaction part, it starts from here. What do I need for this? I need here sodium hydroxide in the presence of water, and I'll also be looking here at triethylene glycol. I'll just write TREG, triethylene glycol. It's not even official, I'm just writing it as this, and in the presence of a strong heat. When you do this reduction process, your end result will be this. Look, you started here with methyl cyclohexane ketone, you'll end here with a CH2 and CH3. You can just say ethyl cyclohexane, and your byproducts will be what? You'll have here diatomic nitrogen. That diatomic nitrogen is coming right from here, the N and the N. These two hydrogen molecules will come off here as a water molecule. You'll also have the water molecule coming here. You know what? I'll demonstrate this as an intermediate step over here. But then when you took it further, you're also regenerating your base, your hydroxide, and here is your end result. And everything comes to an end. What are your main reactants? Your main reactants are a ketone, hydrazine. For this initial step, for the second step, your main reactants are sodium hydroxide, water. These alcohols and triethylene glycols are just reaction mediums. Your byproducts are your alkane. It is an alkane. It's a cyclohexane with an ethane, ethyl cyclohexane, and hydroxide and diatomic nitrogen. These are your byproducts. This right here is your end result. You've converted a carbonyl into a CH2, and everything is good. Thank you for watching.